CIET NCERT presents audiobook Ganit Prakash, textbook of mathematics for grade 8.
Chapter number 5, Number Play. Page number 112. On the right side of the page, you are provided with a QR code, scanning which you can reach out to the additional resources of this chapter. 5.1. Is this a multiple of? Sum of consecutive numbers. Anshu is exploring sums of consecutive numbers. He has written the following. 7 is equal to 3 plus 4. 10 is equal to 1 plus 2 plus 3 plus 4. 12 is equal to 3 plus 4 plus 5. 15 is equal to 7 plus 8. Or 15 is equal to 4 plus 5 plus 6. Or 15 is equal to 1 plus 2 plus 3 plus 4 plus 5. Now, he is wondering, can I write every natural number as a sum of consecutive numbers? Which numbers can I write as the sum of consecutive numbers in more than one way? Oh, I know all odd numbers can be written as a sum of two consecutive numbers. Can we write all even numbers as a sum of consecutive numbers? Can I write 0 as a sum of consecutive numbers? Maybe I should use negative numbers. Explore these questions and any others that may occur to you. Discuss them with the class. Take any 4 consecutive numbers, for example 3, 4, 5 and 6. Place plus and minus signs in between the numbers. How many different possibilities exist? Write all of them. 3 plus 4 minus 5 plus 6. 3 minus 4 minus 5 minus 6. Page number 113. 8 such expressions are possible. You can use the diagram given here to systematically list all the possibilities, like 3 plus 4 plus 5 plus 6 or 3 plus 4 plus 5 minus 6, 3 plus 4 minus 5 plus 6, 3 plus 4 minus 5 minus 6, or 3 minus 4 plus 5 plus 6, or 3 minus 4 plus 5 minus 6, or 3 minus 4 minus 5 plus 6, or 3 minus 4 minus 5 minus 6. Evaluate each expression and write the result next to it. Do you notice anything interesting? Now, take 4 other consecutive numbers. Place the plus and minus signs as you have done before. Find out the results of each expression. What do you observe? Repeat this for one more set of 4 consecutive numbers. Share your findings. 3 plus 4 minus 5 plus 6 is equal to 8. 3 minus 4 minus 5 minus 6 is equal to minus 12. 5 plus 6 minus 7 plus 8 is equal to 12. 5 minus 6 minus 7 minus 8 is equal to minus 16. And so on. Some sums appear always no matter which 4 consecutive numbers are chosen. Isn't that interesting? Do these patterns occur no matter which 4 consecutive numbers are chosen? Is there a way to find out through reasoning? Hint: use algebra and describe the 8 expressions in a general form. You might have noticed that the results of all expressions are even numbers. Even numbers have a factor of 2. Negative numbers having a factor 2 are also even numbers. For example, -2, -4, -6 and so on. Check if anyone in your class got an odd number. When 4 consecutive numbers are chosen, no matter how the plus and minus signs are placed between them, the resulting expressions always have even parity. Page number 114. Now take any 4 numbers, place plus and minus signs in the 8 different ways and evaluate the resulting expression. What do you observe about their parities? Repeat this with other set of 4 numbers. Is there a way to explain why this happens? Hint: think of the rules for parity of the sum or difference of 2 numbers. Explanation 1. Let us consider any of the 8 expressions formed by 4 numbers A, B, C and D. When one of its signs is switched, its value always increases or decreases by an even number. Let us see why. Consider one of the expressions A plus B minus C minus D. Replacing plus B by minus B, we get A minus B minus C minus D. By how much has the number changed? It has changed by A plus B minus C minus D within brackets minus A minus B minus C minus D within brackets. That is equal to A plus B minus C minus D minus A plus B plus C plus D. Notice how the signs changed when we open the second set of brackets. That is equal to 2b. This is an even number. If the difference between 2 numbers is even, can they have different parities? No. So, either both are even or both are odd. Now, let us see what happens when a negative sign is switched to a positive sign. Replace any negative sign in the expression A plus B minus C minus D with a positive sign and find the difference between the 2 numbers. What do you conclude from this observation? Starting from any expression, we can get 7 expressions by switching one or more plus and minus signs. Thus, all the expressions have the same parity. Explanation 2. We know that odd plus or minus odd is equal to even. Even plus or minus even is equal to even. Odd plus or minus even is equal to odd. We have seen that the parity of A plus B and A minus B is the same, regardless of the parities of A and B. In short, A plus or minus B have the same parity. By the same argument, A plus or minus B plus C and A plus or minus B minus C have the same parity. Extending this further, we can say that all the expressions A plus or minus B plus or minus C plus or minus D have the same parity. Page number 115. Explanation 3. This can also be explained using the positive and negative token model you studied in the chapter on integers. Try to think how. The number of ways to choose 4 numbers A, B, C and D and combine them using plus and minus signs is infinite. Mathematical reasoning allows us to prove that all the combinations A plus minus B plus minus C plus minus D always have the same parity without having to go through them one by one. On the right side of the page, a pictorial representation of the same has been explained as a plus b plus c plus d, or a plus b plus c minus d, a plus b minus c plus d, or a plus b minus c minus d, or a minus b plus c plus d, a minus b plus c minus d, a minus b minus c plus d, or a minus b minus c minus d. Several problems in mathematics can be thought about and solved in different ways. While the method you came up with may be dear to you, it can be amusing and enriching to know how others thought about it. 2 tidbits. Share and listen. Is the phenomenon of all the expressions having the same parity limited to taking 4 numbers? What do you think? What if? Will it always happen? Wondering and posing questions and conjectures is as much a part of mathematics as problem solving. Breaking even. We know how to identify even numbers. Without computing them, find out which of the following arithmetic expressions are even. 43 plus 37. 672 minus 348. 4 into 347 into 3. 708 minus 477. 809 plus 214. 119 into 303. 543 minus 479. 513 whole cube. Using our understanding of how parity behaves under different operations, identify which of the following algebraic expressions give an even number for any integer values for the letter numbers. 2a plus 2b, 3g plus 5h, 4m plus 2n, 2u minus 4v, 13k minus 5k, 6m minus 3n, x square plus 2, b square plus 1, 4k into 3j. Page number 116. The expression 4m plus 2q will always evaluate to an even number for any integer values of m and q. We can justify this in 2 different ways. We know 4m is even and 2q is even for any integers m and q. Therefore, their sum will also be even. The expression 4m plus 2q is equal to the expression 2 within brackets 2m plus q. Here, the expression 2 within brackets 2m plus q means 2 times 2m plus q. In other words, 2 is a factor of this expression. Therefore, this expression will always give an even number for any integers m and q. For example, if m is equal to 4 and q is equal to minus 9, the expression 4m plus 2q becomes 4 into 4 plus 2 into minus 9, that is equal to minus 2, which is an even number. In the expression x square plus 2, x square is even if x is even and x square is odd if x is odd. Therefore, the expression x square plus 2 will not always give an even number. An example and a non-example for when the expression evaluates to an even number. First one, if x is equal to 6, then x square plus 2 is equal to 38. And second one, If x is equal to 3, then x square plus 1 is equal to 11. Similarly, determine and explain which of the other expressions always give even numbers. Write a couple of examples and non-examples as appropriate for each expression. Write a few algebraic expressions which always give an even number. Pairs to make fours. Take a pair of even numbers. Add them. Is the sum divisible by 4? Try this with different pairs of even numbers. When is the sum a multiple of 4 and when it is not? Is there a general rule or a pattern? Even numbers can be of two types based on the remainders they leave when divided by 4. Here we have two different pictures. In the first picture, we are provided with 4 blue circles in a row on the top, and at the bottom again we have 4 blue balls in the last row. Even numbers that are multiples of 4 leave a remainder of 0 when divided by 4. In the next picture, we have 4 blue circles in the first row and 4 blue circles in the bottom row, and below that 2 blue more circles are there. Even numbers that are not multiples of 4 leave a remainder 2 when divided by 4. Page number 117. When will two even numbers add up to give a multiple of 4? This problem is similar to the question of identifying when adding two numbers will result in an even number. Can you notice this? There are 3 cases to examine. Here there is a table provided in which explanations with algebra and visualization is given with certain examples. In the first column, we have adding two even numbers that are multiples of 4 will always give a multiple of 4. In the next column, we have 4p and 4q. 4p plus 4q can be written as 4 within brackets p plus q. In the third column, there is a pictorial representation to explain the same, and in the fourth column, we have examples as 4, 12, 16, 24, 36. And 12 plus 16 is equal to 4 within brackets 3 plus 4, taking 4 common. That is equal to 28. Also, 16 plus 28 can be written as 4 is taken common. 4 plus 7 within brackets on simplification gives us 44. In the third column, we are provided with a box which has 4 blue circles in the first row and 4 blue circles in the bottom row with p rows. Plus, there is another box in which we have 4 yellow circles in the top row. Likewise, 4 yellow circles in the bottom row. We have total number of rows as q. When you add them, we get a combination of p plus q rows in which we have 4 blue circles in the top row and 4 blue circles in the bottom row, which is added to 4 yellow balls in the first row and 4 yellow balls in the bottom row. In the next row, we have adding two even numbers that are not multiples of 4 will always give a multiple of 4 because their remainders of 2 add up to 4. In the second column, it has been expressed as 4p plus 2 and 4q plus 2. 4p plus 2 within brackets plus 4q plus 2 within brackets can be expressed as 4p plus 4q plus 4. Taking 4 common, we can write it as 4 within brackets p plus q plus 1. The pictorial representation has been done in the third column as 4 blue balls in the first row and 4 blue balls in the bottom row with 2 more balls in the last row. It is having p rows. Plus, we have 4 yellow balls in the first row, 4 yellow balls in the bottom row, plus 2 yellow balls in the last row. This has q rows, which can be added, and it can be observed that we have 4 blue balls in the top row, 4 blue balls in the bottom row with 2 blue balls and 2 yellow balls, making 4 balls here again, and 4 yellow balls in the second row and 4 yellow balls in the last row. Thus we have p rows plus 1 row formed by 2 blue and 2 yellow circles and q rows. Thus we have p plus q plus 1 rows here. And the examples mentioned are in the last column as 2, 6, 10, 18, 22, 42, which can be expressed as 2 plus 6 is equal to 8, 6 plus 10 is equal to 16, 22 plus 6 is equal to 28. What happens when we add a multiple of 4 to an even number that is not a multiple of 4? Is it similar to the case of the parity of the sum of an even and an odd number? Notice the following expressions and the visualization. Write the corresponding explanation and examples. Page number 118. Explanations with algebra and visualization have been explained here. We have in the second column 4p and 4q plus 2, that is equal to 4p plus within brackets 4q plus 2, that can be written as 4p plus 4q plus 2, that is equal to 4 is taken common. We have p plus q in brackets plus 2. In the third column, we have a box in which 4 circles which are blue in color are there in the first row and 4 blue circles are in the bottom row, forming p rows. Plus, we have another box in which we have 4 yellow circles in the first row, 4 yellow circles in the last row, and below that we have 2 more yellow balls forming q rows. When added, we get 2 boxes in which we have 4 blue balls in the first row, 4 blue balls in the last row. When added to 4 yellow balls in the first row, 4 yellow balls in the bottom row, and 2 more yellow balls in the same box. So we have p plus q rows with a remainder 2. Notice how we are able to generalize and prove properties of arithmetic using algebra and also using visualization. Always, sometimes, or never. We examine different statements about factors and multiples and determine whether a statement is always true, sometimes true, or never true. We know that the sum of any 2 multiples of 2 is also a multiple of 2. Question number 1. If 8 exactly divides 2 numbers separately, it must exactly divide their sum. Explanation with algebra and visualization has been explained in the table with the help of examples. The 2 numbers have 8 as a factor. In other words, the 2 numbers are multiples of 8. In the second column, we have 8a and 8b. We are also given examples in the last column 8 and 16, 16 and 56, 80 and 120. In the next row, as multiples of 8 are obtained by repeatedly adding 8, the sum of 2 multiples of 8 will also be a multiple of 8. In the second column, we have 8a plus 8b, that is equal to 8 outside the brackets, and inside the brackets we have a plus b. In the third column, there is a pictorial representation in which we have 8 blue balls in the first row and 8 blue balls in the last row. They are A rows in total, and we have 8 yellow balls in the first row and 8 yellow balls in the last row, thus forming B rows. On adding these, we have A plus B rows. For examples, we have 8 plus 16 is equal to 8 is common, so we have 1 plus 2 within brackets, that is equal to 24. 16 plus 56 is equal to 72. 80 plus 120 is equal to 200. Statement 1 is always true. Determine if it is true with subtraction. Page number 119. In general, if A divides M and A divides N, then A divides M plus N and A divides M minus N. In other words, if M and N are multiples of A, then M plus N and M minus N will also be multiples of A. Question number 2. If a number is divisible by 8, then 8 also divides any two numbers separately that add up to the number. Here we have a tabular column in which explanation with algebra and visualization is given along with the examples. In the first column, we have a number divisible by 8 is a multiple of 8. In the next column, we have 8 into m, 8m. And in the example column, we have 8, 16, 56, 72. Below that, in the next row, we have in the first column, a number divisible by 8 can be expressed as a sum of two multiples of 8 or sum of two non-multiples of 8. In the next column, 8m is equal to 8a plus 8b. 8m is equal to p plus q, where p and q not multiples of 8. In the next column, we have pictorial representation of the same. In the first row, we have blue 8 circles, and in the last row, we have 8 blue circles, thus we have a number of rows. And in the next box, we have 8 blue circles in the top row and 8 blue circles in the bottom row. Thus we have B rows. On adding, we have M is equal to A plus B rows. That is equal to, we have 8 blue circles into P, and we also have 8 blue circles in the bottom row as Q. Examples mentioned along with this are 72 is equal to 48 plus 24, that is equal to 8 into 9 is equal to 8 into 6 plus 8 into 3. Also 72 is equal to 50 plus 22. So statement 2 is sometimes true. Question number 3. If a number is divisible by 7, then all multiples of that number will be divisible by 7. Explanation with algebra and visualization have been explained in the tabular form along with the examples. First column reads, numbers divisible by 7 will have 7 as a factor. In the second column, we have 7j. And examples are 14 is equal to 7 into 2, within brackets j is equal to 2. 42 is equal to 7 into 6, within brackets j is equal to 6. 98 is equal to 7 into 14, within brackets j is equal to 14. In the next row, we have this contains a total of mj rows. So, This is also a multiple of 7. In the second column, we have 7j within brackets multiplied by m. This has been explained with the help of picture in the third column as 7 balls in the first row, 7 balls in the last row, thus forming j rows, and 7 balls which are blue in color in the first row and 7 blue balls in the bottom row forming j rows, and also we have one more box with 7 blue balls in the top row and 7 blue balls in the bottom row in j rows. Combining all this, we have m times. So examples are some multiples of 14 are 28 is equal to within bracket 7 into 2 into 2. 70 is equal to within brackets 7 into 2 into 5. 154 is equal to within brackets 7 into 2 into 11. The number 7jm or 7 into j into m within brackets has a factor of 7. We can notice that statement 3 is always true. Page number 120. In general, if a is divisible by k, then all multiples of a are divisible by k. Question number 4. If a number is divisible by 12, then the number is also divisible by all the factors of 12. Explanation with algebra and visualization is given in the tabular form along with the examples. The first column reads, a number divisible by 12 is a multiple of 12. In the second column, we have 12m, and examples mentioned are 12, 24, 36, 48, 108 and 132. In the next row, it is mentioned that factors of multiples of 12 will include factors of 12. In the second column, 12m is equal to 2 into 6 into m, that is equal to 3 into 4 into m. In the third column, there is a pictorial representation of 12 balls in the first row and 12 blue balls in the last row. We have m number of rows here, and it is mentioned that a factor of 12 covers a row fully. Hence, it covers all multiples of 12 fully. Examples mentioned along with this are factors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. In general, if a is divisible by k, then a is divisible by all the factors of k. Hence, statement 4 is always true. Question number 5. If a number is divisible by 7, then it is also divisible by any multiple of 7. Explanation with algebra and visualization has been given in the table, and examples are also mentioned. In the first column, numbers divisible by 7 are multiples of 7. In the second column, 7 into k is written. In the third column, we have 7 blue balls in the first row and 7 blue balls in the last row. Thus, we have k rows. In the next row, we have multiples of 7. 7k will be divisible by 7m if and only if m is a factor of k. In the second column, we have 7m. If k is equal to ym, then 7k divided by 7m is equal to 7ym divided by 7m, that is equal to y. In the third column, we have pictorial representation of the same. In the first box, we have 7 blue balls in the first row and 7 blue balls in the last row, thus forming M rows. And adjacent to this, we have again 7 balls in the first row and 7 blue balls in the last row, thus forming M rows. Likewise, we have 7 blue balls in the first row and 7 blue balls in the last row, representing M rows. So, we have in total K rows. In examples, we have 42 within bracket 7 into 6 is divisible by 7, but it is not divisible by 28. The factors of 28 are written in the bracket 7 into 4. 42, we have factors as 7 into 6 in brackets is divisible by 7 and it is divisible by 14 within brackets 7 into 2. We can notice that this statement is only sometimes true. Page number 121. Examine each of the following statements and determine whether it is always true, sometimes true, never true. Question number 6. If a number is divisible by both 9 and 4, it must be divisible by 36. Question number 7. If a number is divisible by both 6 and 4, it must be divisible by 24. In general, if A is divisible by K and A is also divisible by M, then A is divisible by the LCM of K and M. This is because A is a multiple of K and also a multiple of M. So, A's prime factorization should contain the prime factorization of LCM within brackets K, M. Question number 8. When you add an odd number to an even number, we get a multiple of 6. We know that multiples of 6 are all even numbers. The sum of an odd number and an even number will be an odd number. Therefore, this statement is never true. We can also explain this algebraically. Suppose 2n within brackets plus 2m plus 1 within brackets is equal to 6j, where 2n is an even number, 2m plus 1 is an odd number and 6j is a multiple of 6. Then 2n plus 2m is equal to 6j minus 1. That is equal to 2 within brackets n plus m is equal to 6j minus 1, which means 2 within brackets n plus m, which is an even number, should be equal to 6j minus 1, which is an odd number. This is never true. There is a picture of a boy saying, "Can I write an even and an odd number as 2n and 2n plus 1 instead?" What remains? Question. Find a number that has a remainder of 3 when divided by 5. Write more such numbers. Which algebraic expressions capture all such numbers? First one, 3k plus 5. Second one, 3k minus 5. Third one, 3k divided by 5. Fourth one, 5k plus 3. Fifth one, 5k minus 2. Sixth one, 5k minus 3. The numbers that leave a remainder of 0 when divided by 5 are the multiples of 5. But we want numbers that leave a remainder of 3 when divided by 5. These numbers are 3 more than multiples of 5. Multiples of 5 are of the form 5k. So, numbers that leave a remainder of 3 when divided by 5 are those of the form 5k plus 3. Here we have a pictorial representation of the same. We have 5 yellow balls in a row, and there are k such rows. We have 5 balls in the last row and 3 balls which are yellow in the bottom row. We also have the value k mentioned as 0, 1, 2, 3, 4, and 5k plus 3 is written as 3, 8, 13, 18, 23. Page number 122. Let us consider another expression 5k minus 2 and observe the values it takes for different values of k. Numbers that leave a remainder of 3 when divided by 5 can also be seen as 2 less than multiples of 5, that is 5k minus 2, where k is greater than or equal to 1. Are there other expressions that generate numbers that are 3 more than a multiple of 5? Here we have a tabular column in which the values of k are 1, 2, 3, 4 and 5, and corresponding values of 5k minus 2 are 3, 8, 13, 18 and 23 respectively. Figure it out. Question number 1. The sum of 4 consecutive numbers is 34. What are these numbers? Question number 2. Suppose p is the greatest of 5 consecutive numbers. Describe the other 4 numbers in terms of p. Question number 3. For each statement given here, determine whether it is always true, sometimes true, or never true. Explain your answer. Mention examples and non-examples as appropriate. Justify your claim using algebra. First one, the sum of 2 even numbers is a multiple of 3. Second one, if a number is not divisible by 18, then it is also not divisible by 9. Third one, if 2 numbers are not divisible by 6, then their sum is not divisible by 6. Fourth one, the sum of a multiple of 6 and a multiple of 9 is a multiple of 3. Fifth one, the sum of a multiple of 6 and a multiple of 3 is a multiple of 9. Question number 4. Find a few numbers that leave a remainder of 2 when divided by 3 and a remainder of 2 when divided by 4. Write an algebraic expression to describe all such numbers. Question number 5. I hold some pebbles, not too many. When I group them in threes, one stays with me. Try pairing them up. It simply won't do. A stubborn odd pebble remains in my view. Group them by 5, yet one still around, but grouping by 7, perfection is found. More than 100 would be far too bold. Can you tell me the number of pebbles I hold? On the right side, there is a cartoon of a pot with 2 hands and some pebbles around. Question number 6. Tathagat has written several numbers that leave a remainder of 2. When divided by 6, he claims if you add any 3 such numbers, the sum will always be a multiple of 6. Is Tathagat's claim true? Page number 123. Question number 7. When divided by 7, the number 661 leaves a remainder of 3 and 4779 leaves a remainder of 5. Without calculating, can you say what remainders the following expressions will leave when divided by 7? Explain the solutions both algebraically and visually. First one, 4779 plus 661. Second one, 4779 minus 661. Question number 8. Find a number that leaves a remainder of 2 when divided by 3, a remainder of 3 when divided by 4, and a remainder of 4 when divided by 5. What is the smallest such number? Can you give a simple explanation of why it is the smallest? 5.2. Checking divisibility quickly. Earlier, you have learnt shortcuts to check whether a given number written in the Indian number system is divisible by 2, 4, 5, 8 and 10. Let us revisit them. Divisibility by 10, 5 and 2. If the units digit of a number is 0, then it is divisible by 10. Let us understand why this works through algebra. We can write the general form of a number in the Indian system using set of letter numbers. For example, a 5-digit number can be expressed as EDCBA, denoting E into 10,000 plus D into 1,000 plus C into 100 plus B into 10 plus A. The letter numbers E, D, C, B and A denote each digit of a 5-digit number. Any number can be written in general as DCBA, where the letter numbers A, B, C and D represent the units, tens, hundreds and thousands digit respectively, and so on. As a sum of place values, this number is plus 1000D plus 100C plus 10B plus A. For example, in the number 4075, D is equal to 4, C is equal to 0, B is equal to 7 and A is equal to 5. We know that each place value, with the exception of the units place, is a multiple of 10. So, 10B, 100C and so on, all will be multiples of 10. Hence, the number will be divisible by 10 if and only if the units digit A is 0. Similarly, explain using algebra why the divisibility shortcuts for 5, 2, 4 and 8 work. Let us now examine shortcuts to check divisibility by some other numbers and explain why they work. A shortcut for divisibility by 9. Can you say, without actually calculating, which of these numbers are divisible by 9? 999, 909, 900, 90, 990. All of them. Page number 124. Can we say that any number made up of only the digits 0 and 9 in any order will always be divisible by 9? Yes, if each digit is either 0 or 9, then each term in its expanded form will be 9 multiplied by dash or 0 multiplied by dash. The dash denotes a place value. This means each term will be a multiple of 9. For example, 99,009 is equal to 9 multiplied by 10,000 plus 9 into 1000 plus 0 into 100 plus 0 into 10 plus 9 into 1. But this shortcut alone cannot identify all the multiples of 9. Unlike the numbers 2, 5 and 10, we cannot identify the multiples of 9 by just looking at the units digit. 99 and 109 are two numbers with 9 as the units digit. But 99 is divisible by 9 while 109 is not. Is 10 divisible by 9? If not, what is the remainder? Check the divisibility of other multiples of 10. Within brackets 10, 20, 30 and so on by 9. You will notice that for any multiple of 10, the remainder is the same as the number of tens. We also have some colorful pictures with 99 in blue and 1 in yellow. Again we have another one representing 99 in blue and 1 in yellow. In addition to this, we have 9 in green color with 1 attached to it in yellow color. We have 9 digit in green with 1 attached to it in yellow. One more in green with digit 9 in it and 1 attached to it in yellow. You will notice that for any multiple of 10, the remainder is the same as the number of tens. Similarly, look at the remainder when the multiples of 100 brackets 100, 200, 300 and so on close the bracket are divided by 9. What do you notice? The remainder is the same as the number of hundreds for any multiple of 100. Using this observation, find the remainder when 427 is divided by 9. This has been explained with the help of picture here. We have 400 represented as with 4 units of 100 with 99 and 1 separately in different colors in blue and 1 in yellow. 99 in blue and 1 in yellow. 99 in blue with 1 in yellow and 99 in blue with 1 in yellow. And for 20 we have 9 in green, 1 attached to it in yellow. Similarly, one more 9 in green with 1 attached to it in yellow. And 7 is represented with the help of 7 tokens which are yellow in color. We see that 427 has 4 hundreds. Thus, its corresponding remainder upon division by 9 would be 4. 427 has 2 tens and its corresponding remainder would be 2. We have 7 units also remaining. Adding all the remainders, we get 4 plus 2 plus 7 is equal to 13. We can make one more group of 9 with 13, leaving a remainder of 4. Therefore, 427 when divided by 9 gives a remainder of 4. This has been again explained with the help of picture in which we have 4 99s plus 4 units which are yellow in color and we have 2 green units with 1 attached to them, and also we have 7 units of 1 yellow tokens, and when we combine 4 unit tokens yellow in color along with 9 tokens which are yellow in color, they represent 4 as remainder. Page number 125. Will this work with bigger numbers? You can observe that this is true for any place value. 1 is equal to 0 plus 1, 10 is equal to 9 plus 1, 100 is equal to 99 plus 1, 1000 is equal to 999 plus 1, 10,000 is equal to 9,999 plus 1, and so on. Each digit thus denotes the remainder when the corresponding place value is divided by 9. Here we have different colored tokens with 999 and 1 as yellow token, and 9,999 with 1 as yellow token, 99 with a blue token and a 1 token attached to it which is yellow in color. So there is a green token with 9 in it and unit of 1 token attached to it which is yellow in color. For example, to find the remainder of 7,309 when divided by 9, we can just add all the digits 7 plus 3 plus 0 plus 9 to get 19. This can be observed as follows. We have 7 into 1000 which has been represented with the help of purple 7 tokens of 999 each and 1 token of yellow attached to each of these 7 purple tokens. So it represents 7 into 1000. Likewise, for 3 into 100, we have 3 tokens which are blue in color and they have 1 attached to it in the form of yellow token. 9 into 1, we have 9 unit tokens which are yellow in color. Likewise, we have 7 into 999 with 7 purple tokens here and 3 into 99, that is 3 into blue tokens which are representing 99. We also have this unit token separately collected as 7 from the first one and 3 from the second blue tokens and 9 tokens which were separately collected here, and we can find that you need to just consider this part as 7 plus 3 plus 9, that is equal to 19. And for purple and blue, this is a multiple of 9. That can be explained as 7 into 1000 plus 3 into 100 plus 0 into 10 plus 9 into 1. This can be written as 7 into within brackets 999 plus 1 plus 3 into 99 plus 1 within brackets plus 0 into 9 plus 1 within brackets plus 9 into 0 plus 1 within brackets. That is equal to 7 into 999 plus 3 into 99 plus 0 into 9 plus 9 into 0 within brackets plus 7 into 1 plus 3 into 1 plus 0 into 1 plus 9 into 1 all in brackets. That is equal to, we have within brackets 7 into 999 plus 3 into 99 plus 0 into 9 plus 9 into 0. All this is in brackets. It is showing that it is multiple of 9 plus 7 plus 3 plus 0 plus 9. All this is in brackets. So we need to just consider this part. This means that the number 7,309 is 19 more than some multiple of 9. The digits 1 and 9 can further be added to get 1 plus 9 is equal to 10. Now, we can say that 7,309 is 10 more than a multiple of 9, and repeating this step for the number 10, we get the remainder to be 1 plus 0 is equal to 1, meaning 7,309 is 1 more than a multiple of 9. Therefore, 7,309 divided by 9 gives a remainder of 1. A number is divisible by 9 if and only if the sum of its digits is divisible by 9. Also, we can add the digits of a number repeatedly till the single digit is obtained. This single digit is the remainder when the number is divided by 9. Notice each of the following statements, which are correct and why. First one, if a number is divisible by 9, then the sum of its digits is divisible by 9. Page number 126. Second one, if the sum of the digits of a number is divisible by 9, then the number is divisible by 9. Third one, if a number is not divisible by 9, then the sum of its digits is not divisible by 9. Fourth one, if the sum of the digits of a number is not divisible by 9, then the number is not divisible by 9. Learning maths is not just about knowing some shortcuts and following procedures, but also understanding why something works. Figure it out. First one, find without dividing whether the following numbers are divisible by 9. First one, 123. Second one, 405. Third one, 8,888. Fourth one, 93,547. Fifth one, 3,58,095. Question number 2. Find the smallest multiple of 9 with no odd digits. Question number 3. Find the multiple of 9 that is closest to the number 6,000. Fourth one. How many multiples of 9 are there between the numbers 4,300 and 4,400? A shortcut for divisibility by 3. We know that all the multiples of 9 are also multiples of 3. That is, if a number is divisible by 9, it would also be divisible by 3. However, there are other multiples of 3 that are not multiples of 9. For example, 15, 33 and 87. The shortcut to find the divisibility by 3 is similar to the method for 9. A number is divisible by 3 if the sum of its digits is divisible by 3. Explore the remainders when powers of 10 are divided by 3. Explain why this method works. A shortcut for divisibility by 11. Interestingly, the shortcut for 11 is also based on checking the remainders with place value. Let us observe how. Page number 127. Here we have 4 tabular columns. In the first one, we have unit place as 1. In the second column, we have 11 into 0 is equal to 0. 1 is equal to 11 into 0 plus 1. In the third column, 1 is 1 more than a multiple of 11. And in the last column, we have 1 circle. In the second row, tens place, 10 is written in brackets. In the next column, 11 into 1 is equal to 11, or 10 is equal to 11 into 1 minus 1. Third column has 10 is 1 less than a multiple of 11. And in the last column, we have 11 circles inside a encircled area representing 11 circles. Third row has hundreds place, that is 100 within brackets. In the next column, 11 into 9 is equal to 99. 100 is equal to 11 into 9 plus 1. In the third column, 100 is 1 more than a multiple of 11. In the last column, we have 11 circles which are 9 times and one more circle outside the box, thus representing 11. In the next row, we have thousands place, within brackets 1000. Next column has 11 into 99 is equal to 1001, or 1000 is equal to 11 into 91 minus 1. In the third column, 1000 is 1 less than a multiple of 11. And in the last column, we have pictorial representation of the same. We have 11 circles in a row, which are 91 times, so which are 11 in number. This alternating pattern of 1 more than 11 and 1 less than 11 continues for higher place values. Since 400 contains 4 hundreds, 400 is 4 more than a multiple of 11, that is 396 plus 4. Since 60 contains 6 tens, 60 is 6 less than a multiple of 11, within brackets 66 minus 6. Since 2 contains 2 units, 2 is 2 more than a multiple of 11, that is 2 is equal to within brackets 0 plus 2. Next question. Using these observations, can you tell whether the number 462 is divisible by 11? What could be a general method or shortcut to check divisibility by 11? Page number 128. We observe that the place values alternate as 1 more and 1 less than a multiple of 11. Using this information, we have a explanation given here in columns. First column represents steps, second column represents purpose, and third column represents example for the number 320185. In the first column, we have add the digits of a place values which are 1 more within brackets than a multiple of 11, that is place values corresponding to 1, 100, 10,000 and so on. The purpose is to know how much in excess we are with respect to a multiple of 11 for these place values. In the pictorial representation, for the example for the number 320185, we have 2 into 10,000 represented with the help of 909 11s. Same way, we have another one with 909 11s in another box, and 1 into 100 which is represented with the help of 11 circles 9 times, and likewise we have 5 into 1 as 5 circles given on the right side. So total excess is 2 plus 1 plus 5, that is equal to 8. In this pictorial representation, we notice that there is one circle given outside the box in every representation. Second one, add the digits of place values which are 1 less than a multiple of 11, that is, place values corresponding to 10, 1000, 1 lakh and so on. Purpose is to know how short we are with respect to a multiple of 11 for these place values. For the number 320185, the pictorial representation has been explained here. We have 3 into 10,000 as 3 times we have 9091 in 11 circles arranged in a row, and we also have a red circle inside all the 3 such arrangements. For 0 into 100, we have 11 circles with 1 red circle in each representation, and for 8 into 10, we have 11 such circles with 1 red circle in each such arrangement. So total short 3 plus 0 plus 8, that is equal to 11. Third one, compute the difference between these two sums, that is number in excess minus number short. Purpose is to know the remainder obtained when divided by 11. In the third column, we have a representation of 8 green circles and 11 red circles, meaning 8 minus 11 is equal to minus 3. That is 3 short of a multiple of 11. The difference between these two sums, 8 minus 11 is equal to minus 3, indicating that the number 3, 28, 105 is 3 short of or 8 more than a multiple of 11. If this difference is 11 or a multiple of 11, what does that say about the remainder obtained when the number is divisible by 11? Using this shortcut, find out whether the following numbers are divisible by 11. Further, find the remainder if the number is not divisible by 11. First one, 158. Second one, 841. Third one, 481. Fourth one, 5529. Fifth one, 90,904. Sixth one, 857076. Page number 129. Study the following procedures. Steps to follow and example for the number 328105. We have 2 different columns here. In the first column, we have first point, place alternating plus and minus signs before every digit starting from the units digit. Example, minus 3 plus 2 minus 8 plus 1 minus 0 plus 5. Second step, evaluate the expression. Minus 3 plus 2 minus 8 plus 1 minus 0 plus 5 is equal to minus 3. Third step, the result denotes the remainder obtained when the number is divided by 11. Example, 328105 is 3 less than or 8 more than a multiple of 11. Is this method similar to or different from the method we saw just before? Fill in the following table. Find a quick way to do this. We have a tabular column in which we have set of some numbers, and on the right side we have divisibility by the numbers 2, 3, 4, 5, 6, 8, 9, 10 and 11 mentioned in various columns. The numbers to be checked for divisibility are 128, then 990, Next, 1586, 275, 6686. Then we have 639210. Next, 429714. In the next row, 2856. In the next row, 3060. And in the last row, we have 406839. More on divisibility shortcuts. Divisibility shortcuts for other numbers. How can we find out if a number is divisible by 6? Will checking its divisibility by its factors 2 and 3 work? Use the shortcuts for 2 and 3 on these numbers and divide each number by 6 to verify 38, 225, 186, 64. Page number 130. How about checking divisibility by 24? Will checking the divisibility by its factors 4 and 6 work? Why or why not? Determining divisibility by 24 by checking divisibility by 4 and by 6 does not work. For example, the number 12 is divisible by both 4 and 6 but not by 24. To check for the divisibility by 24, we can instead check for the divisibility by 3 and divisibility by 8. Explain using prime factorization why checking divisibility by 3 and 8 works for checking divisibility by 24. But checking divisibility by 4 and 6 is not sufficient for checking divisibility by 24. There are such shortcuts to check divisibility by every number until 100 and for some numbers beyond 100. You may try to understand how these work after learning certain concepts in higher grades. Digital roots. Take a number, add its digits repeatedly till you get a single digit number. This single digit number is called the digital root of the number. For example, the digital root of the number 489710 will be 2 within brackets 4 plus 8 plus 9 plus 7 plus 1 plus 0 is equal to 29. 2 plus 9 is equal to 11 and 1 plus 1 is equal to 2. What property do you think this digital root will have? Recall that we did this while finding the divisibility shortcut for 9. Between the numbers 600 and 700, which numbers have the digital root? First one 5, second 7, third one 3. Write the digital roots of any 12 consecutive numbers. What do you observe? We observe that the digital root of multiples of 9 is always 9. Now, find the digital roots of some consecutive multiples of first 3, second 4 and third 6. Next question. What are the digital roots of numbers that are 1 more than a multiple of 6? What do you notice? Try to explain the patterns noticed. Next question. I am made up of digits, each tiniest and odd. No shared ground with root. #1. How odd. My digits count. Their sum. My root. All point to 1 bold numbers pursuit. The largest odd single digit I proudly claim. What's my number? What's my name? Here there is a picture with numbers as 10,584, 10,001. Digital Root Club is mentioned on this board, and we have 1001, 111 and 110 are the members written over here. Page number 131. Aryabhatta seconds C 950 CE work Mahasiddhanta mentions the method of computing the digital root of a number by repeatedly adding the digits till a single digit number is obtained. This method is known to have been used to perform checks on calculations of arithmetic operations. Figure it out. Question number 1. The digital root of an 8-digit number is 5. What will be the digital root of 10 more than that number? Question number 2. Write any number. Generate a sequence of numbers by repeatedly adding 11. What would be the digital root of this sequence of numbers? Share your observations. Question number 3. What will be the digital root of the number 9a plus 36b plus 13? Question number 4. Make conjectures by examining if there are any patterns or relations between first one, the parity of a number and its digital root. Next one, the digital root of a number and the remainder obtained when the number is divided by 3 or 9. 5.3 Digits in disguise. Last year, we observed cryptadithms, that is puzzles, where each letter stands for a digit. Each digit is represented by at most one letter, and the first digit of a number is never 0. Solve the cryptadithms given below. First one, A1 plus 1b totals to B0. Second one, AB plus 37 totals to 6A. Third one, ON plus ON plus ON totals to PO. Fourth one, QR plus QR plus QR. Total is PRR. Let us now try solving some cryptadithms involving multiplication. Fifth one, PQ into 8 is equal to RS. Guna says, oh, this means a 2-digit number multiplied by 8 should give another 2-digit number. I know that 10 into 8 is equal to 80, but the units digit of 10 and 80 are the same, which we don't want. For the same reason, PQ cannot be 11 as P and Q corresponds to different digits. 12 into 8 is equal to 96. Fits all the conditions. Can PQ be 13? Think. It is not possible because 13 into 8 is equal to 104. For all 2-digit numbers greater than 12, the product with 8 is a 3-digit number. Here we also have a cute picture of Guna given here on this page. Page number 132. Sixth one. Try this now. GH into H is equal to 9K. This means a 2-digit number multiplied by a 1-digit number gives another 2-digit number in the 90s. Observe the letters corresponding to the units digits in this cryptarithm? Pick the solution to this question from the options given here. 11 into 9 is equal to 99. 12 into 8 is equal to 96. 46 into 2 is equal to 92. 24 into 4 is equal to 96. 47 into 2 is equal to 94. 31 into 3 is equal to 93. 16 into 6 is equal to 96. Question number 7. Here is one more. BYE by into 6 is equal to RAY. Anshu says, since the product is a 3-digit number, B can't be 2 or more. If B is equal to 2, that is 2 hundreds, the product will be more than 1200. So B is equal to 1. Here we have a cute picture of Anshu given here. What can you say about Y? What digits are possible, not possible? Y cannot be 7 or more because if Y is equal to 7, then 170 into 6 is equal to 1020. But we want a 3-digit product. Also, Y will be even. Anshu explains. We can solve cryptarithms using patterns, properties, and reasoning related to numbers and operations. Next question, solve the following. First one, UT into 3 is equal to PUT. Second one, AB into 5 is equal to BC. Third one, L2N into 2 is equal to 2NP. Fourth one, XY into 4 is equal to ZX. Fifth one, PP into QQ is equal to PRP. Sixth one, JK into 6 is equal to KKK. Figure it out. Question number 1. If 31Z5 is a multiple of 9, where Z is a digit, what is the value of Z? Explain why. There are 2 answers to this problem. Question number 2. I take a number that leaves a remainder of 8 when divided by 12. I take another number which is 4 short of a multiple of 12. Their sum will always be a multiple of 8, claims Snehal. Examine his claim and justify your conclusion. Question number 3. When is the sum of 2 multiples of 3 a multiple of 6? And when is it not? Explain the different possible cases and generalize the pattern. Question number 4. Srilatha says, I have a number that is divisible by 9. If I reverse its digits, it will still be divisible by 9. First part, examine if a conjecture is true for any multiple of 9. Second one, are any other digit shuffles possible such that the number formed is still a multiple of 9? Question number 5. If 48A 23B is a multiple of 18, list all possible pairs of values for A and B. Page number 133. Question number 6. If 3P 7Q8 is divisible by 44, list all possible pairs of values for P and Q. Question number 7. Find 3 consecutive numbers such that the first number is a multiple of 2, the second number is a multiple of 3, and the third number is a multiple of 4. Are there more such numbers? How often do they occur? Question number 8. Write 5 multiples of 36 between 45,000 and 47,000. Share your approach with the class. Question number 9. The middle number in the sequence of 5 consecutive even numbers is 5p. Express the other 4 numbers in sequence in terms of p. Question number 10. Write a 6-digit number that is divisible by 15 such that when the digits are reversed, it is divisible by 6. Question number 11. Deepak claims there are some multiples of 11 which, when doubled, are still multiples of 11. But other multiples of 11 don't remain multiples of 11 when doubled. Examine if his conjecture is true. Explain your conclusion. Question number 12. Determine whether the statements below are always true, sometimes true, or never true. Explain your reasoning. First one, the product of a multiple of 6 and a multiple of 3 is a multiple of 9. Second one, the sum of 3 consecutive even numbers will be divisible by 6. Third one, if A, B, C, D, E, F is a multiple of 6, then B, A, D, C, E, F will be a multiple of 6. Fourth one, 8 within brackets 7b minus 3 minus 4 within brackets 11b plus 1 is a multiple of 12. Question number 13. Choose any 3 numbers. When is their sum divisible by 3? Explore all possible cases and generalize. Question number 14. Is the product of 2 consecutive integers always multiple of 2? Why? What about the product of these consecutive integers? Is it always a multiple of 6? Why or why not? What can you say about the product of 4 consecutive integers? What about the product of 5 consecutive integers? Question number 15. Solve the cryptarithms. First one, EF into E is equal to GGG. Second one, WOW into 5 is equal to MEOW. Question number 16. Which of the following Venn diagrams captures the relationship between the multiples of 4, 8 and 32? Page number 134. Here we have Venn diagram representation which are 4 in number. In the first one, we have first oval shape, blue in color, representing multiples of 4. Second oval shape is yellow in color, which represents multiples of 8. And the third oval shape is green in color, which represents multiples of 32. There are some common portions with blue and yellow and green. Likewise, in the second Venn diagram, we have one blue oval shape representing multiples of 4, and there's another oval shape yellow in color representing multiples of 32. The common portion, which is green in color, represents multiples of 8. In the third Venn diagram, we have multiples of 32, which is the largest circle representing green in color. Inside this, we have a yellow color circle which is showing multiples of 8. And inside this, we have a circle, dark green in color, representing multiples of 4. In the fourth Venn diagram, we have the largest circle which is blue in color, representing multiples of 4. Inside this, there is a circle which is placed inside, which is light green in color, representing multiples of 8. Inside this circle, there is another circle which is dark green in color, representing multiples of 32. Summary. We explored and learned various properties of divisibility. First one, if A is divisible by B, then all multiples of A are divisible by B. Next, if A is divisible by B, then A is divisible by all the factors of B. Next, if A divides M and A divides N, then A divides M plus N and M minus N. Next point, if A is divisible by B and is also divisible by C, then A is divisible by the LCM of B and C. Next point, we learned shortcuts to check divisibility by 3, 9 and 11 and why they work. Last point, through all this we were exposed to the power of mathematical thinking and reasoning using algebra, visualization, examples and counterexamples. Page number 135. It's puzzle time. Navakankari. Navakankari, also known as Salu Mane Atta, Char Par or Nav Kakri, is a traditional Indian board game that is the same as Nine Men's Morris or Mills in the West. It is a strategy game for two players where the goal is to form lines of 3 pawns to eliminate the opponent's pawns or block their movement. Here there is a picture of the Navkankari game with 2 sets of pawns which are dark brown in color and 9 in number on the left side, and on the right side we have 9 pawns again which are yellow in color. Gameplay. First point, each player starts with 9 pawns. The player take turns in placing their pawns on the marked intersections. An intersection can have at most 1 pawn. Second, once all the pawns are placed, the players take turns to move one of their pawns to adjacent empty intersections to form lines of 3. The line can be horizontal or vertical. Third, once a player makes a line with their pawns, they can remove any one of the opponent's pawns as long as it is not a part of one of their lines. A player wins if the opponent has less than 3 pawns or is unable to make a move. Here we also have picture of some cute kids. They are wondering at this game Navkankari. Chapter 5 ends here.
Ganit Prakash, you were just listening to this audiobook, textbook of mathematics for grade 8. Narration, Swarnlata Sharma. Sound recordist, Virendra Rawat. Production assistant, Chetna Sharma. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.